this particular problem, I'm just gonna get to the diagram here. If you need to, pause the video, read all this wordy stuff. Other than that, I'm just gonna explain the gist of this problem. Here's a block A, or excuse me, here's a block of 3 kilogram. At point A, it's gonna slide down a frictionless ramp to point B, and then from B, it's gonna go across this rough flat segment to C, and then from C, it is smooth again, and it's gonna compress the spring, and then the spring is gonna get compressed but shoot it back, and it's gonna go across again this rough surface CB now, and then it's gonna go up the ramp again, and then it wants us to find all this different part A, B, and C. All right, other than that, I'm just gonna get cracking. To do part A, it asks you to find the net force on the block as it slides from A to B. Keep in mind from A to B it is frictionless. So here I'm just going to apply the net work function. Net work is equal to net force times displacement. Keep in mind for ramps, we take the surface of the ramp to be our x-axis. Therefore, I'm just going to draw the free body diagram out. Here's f of g, which points down the page. However, it is not in the y-axis because keep in mind the ramp itself is the x-axis. So therefore, f of gy that's going to come up here, it actually is along the y-axis because the y-axis has to be perpendicular to the x-axis. Okay. All right, that's f of gy, and here's theta. Theta here is the same as the theta given the angle of the ramp that touches the horizontal surface, which is in case it is given, that is also the same theta there, which is 35 degrees. But here, I'm just going to draw f of gx pointing down slope, okay, because that's how f of gx does. It always points down slope for these ramp problems. So therefore, f of gx here is parallel to the surface of the ramp. So when you do work, keep in mind your net force has to parallel to the displacement. F of gx parallels the surface of the ramp because both these are in the x-axis. So in this case, the only arrow that I see that is in the x-axis is f of gx. So I'm just going to replace net force with simply f of gx because it is the only force component for this particular problem. All right, on that, I'm just going to expand f of gx to mg sine theta. This is sine theta because according to this angle that's in the diagram, f of gx is the opposite leg. Hence, opposite is sine of theta in geometry. All right, and as you can see here, I know what m is. M is 3 kilogram, g is 9.8. Sine theta, the theta is given as 35 degrees. The only thing I don't know is my delta x. So the height is given though, right? The height of the ramp is given. So therefore, we can actually find the length of the ramp by just doing a little geometry. Here, I'm just going to use sine of 35. Sine of 35 because here's the right triangle, right? Sine of 35 is height, which is the opposite leg, over the hypotenuse, which is the length of the ramp, which I need. All right, on that, here I put sine of 35 equals opposite over delta x. Delta x is what I need to find, so I'm just going to do a little switcheroo. So I'm just going to move delta x up to the top left at the same time. Move the sine of 35 down to the bottom right denominator. Here, my opposite is the height, which is 5 meters, and then sine of 35 degrees. Excuse me. And if you do that correctly, the length of the ramp will be about 8.72 meters, so keep that in mind. Here, I'm just going to go ahead and substitute everything in now that I know delta x. M is 3, g is 9.8, and then sine here is 35 degrees. And then delta x I just found, the length of the ramp is 8.72 meters. And if you simplify it on your calculator, you should get about 147 joules. And that is the answer to part A. However, if you don't want to do all that, and you know the work kinetic energy theorem, which I prefer in this one because I think it's pretty straightforward. Well, here, net work is just the change in kinetic energy, KF minus KI. Well, I can cross out KI because KI is 0 because it starts at rest. So the only thing I need to find is really KF. However, keep in mind, hopefully by now you understand conservation of mechanical energy. At the very, very top of the ramp, the only energy that exists is PE due to gravity. And all that PE will be converted to KE by the time we reach point B. So while I have net work is equal to KEF here in my work, I'm actually going to say KEF is the same as PEI. Well, because it is. All this potential energy initially will be converted to KE by the time it gets to point B. So even though I wrote KF here, I recognize that KF is the same as PE gravity initially. So therefore, the function, oh, by the way, I made a note of this. This is true because it's frictionless, right? There's nothing lost. So hence, mechanical energy is conserved from top to bottom. It just changed form from PE to KE. So therefore, I know PE function is mghi. I know m is 3. I know g is 9.8. I know hi is 5. So therefore, I can just plug everything in. 3 times 9.8 times 5 will give me the same answer, which is 147. So as you see, there's a consistency here. Which method you want to do, that's up to you. All right, let's do part B. Part B is a little more lengthy, so I'll show you how to do this. It says what is the coefficient of kinetic friction between the block and the rough surface between segment B and C. So as it gets to point B, now it's going to go across this flat horizontal surface, which is rough, which means energy will be dissipated. There's some sort of energy loss or work due to friction. Okay. All right. So here we go. Define mu k. By definition, mu k is Fk over Fn. Here, Fn is going to point leftward because the box is moving rightward. And then f of g is pointing down the page, while at the same time Fn is pointing up the page. Keep in mind for this particular segment, f of g is equal to the magnitude of f of n, vice versa. So we can say that Fn is indeed equal to f of g. So by definition, I'm just going to replace Fn with f of g for this particular segment because it's flat and there's no additional forces in the y direction. Okay. Well, but here I know Fg is just mass times acceleration due to gravity. Here, because this is force, I need to plug in negative 9.8 because force has a direction, which makes sense. 3 times the negative number tells me that the arrow is pointing downward. The only thing I'm missing here is f of k, but I can find f of k pretty quickly. Okay, I can use the work kinetic energy theorem. Here, work is equal to the force times displacement. Well, what force? The only force acting horizontally on this box along B to C here is the force of kinetic friction, which points left. It will slow the box down. Okay, well, what's the displacement? The displacement here is just L, which is 5 meters. And then I broke up delta KE into KF minus KI. Here, to solve for f of k, I'm just going to divide both sides by L, which is the length of the segment BC. So I'm going to move L into the denominator on the right side. So here, I have KEF. Now, keep in mind, this is starting at B and then going to C. So KEF is at point C, and then the initial KE is at point B. All right, so this problem starts, or the segment, excuse me, starts at B and it ends at C. So F is C, and then I is B. All right, other than that, I'm just going to go ahead and find KEC and KEB because I already know what L is. L is 5 given in the diagram. So what I can do, excuse me, is use conservation energy, right? From A to B, the slope is frictionless, so we already know that's true. So therefore, PE at the very top must equal to KE at the very bottom at point B. So here I'm going to keep KEB as is because I need KEB and KEC. So I'm just going to go from left to right. From A to B gives me KEB. Well, the energy at point A is just due to potential energy due to gravity, which is just mgha. Here I know m, I know g, I know h, a. I'm just going to plug that in. M being 3, 9.8, h being 5. And then KEB, as we found actually in part A, if you were paying attention, is 147 joules. All right. Now, we know KEB, we know L. The only thing we're missing is KE at point C. Well, this requires a little bit of trick. So just a little bit. Here, it tells us that it's going to compress the spring. So if you think like this, you'll be okay. Well, by the time it gets to point C, from C to the spring is frictionless. So the kinetic energy that it has at point C, all of it must be converted to PE in the spring. So this is my statement. I am saying that the kinetic energy at point C will be transferred or converted to PE in the spring. Okay, because it's going to compress it, right? So therefore, KEC is simply the same as the potential and energy due to the spring because it's just converting kinetic into spring potential. Well, the spring potential function is 1/2 kx squared. I know k is given as 2000. X is 0.3 because it says so here in this particular part B. Other than that, I'm just going to square x. I'm 1 times it by k and then times it by 1/2. So KE at point C is 90 joules, which, I mean, it's reasonable, right? Because it's telling me that the kinetic energy at point B is 147. And then it's going to lose some energy because there's friction. So by the time it gets to point C, there's 90 joules. So the fact that KE at point C is less than KE at point B, this is reasonable. Hopefully my calculator works on. Other than that, I'm just going to plug in KEC for 90 joules and then KEB for 147. So I'm going to take KF, which is 90. I want to subtract it from the initial, which is 147 at the bottom of the ramp, divided by the length of the segment BC, which is 5 meters. And I should get a value of negative 11.4. All right. So I'm just going to plug it back in here. Now that I have Fk, the numerator now, I can be substitute out for just a negative 11.4 newtons. And then 3 times negative 9.8 is negative 29.4. The newtons cancel out, the negative signs cancel out. So therefore, the coefficient of kinetic friction is simply 0.39, or about there. Well, here's another way to do it, right? Same starting point. Mu k is f of k over fn. Right? If you want to, you can break fn into fg like I did. However, what you can do is say that f of k is equal to max, because the only force acting on the box as it travels from B to C is the force of kinetic friction along the surface, which causes it to slow down. So here, I'm just going to say Fk is indeed mass times acceleration, because force is equal to mass times acceleration, and the only force acting on the box from B to C is the force of kinetic friction, which equals to max. As you can see here, mass is going to cancel out. So the only thing I need is ax and g. Well, I already know what g is. G is 9.8. The only thing I'm missing here is ax. So what I can do is use kinematics. I know that I don't have to go through time, right? I know that I can find the acceleration simply by taking vf squared minus vi squared over 2 delta x. Vf being at point C, Vi being at point B. So I'm just going to go ahead and find the two velocities here, because I know delta x is already 5. So even though this function here says delta x, I know that the length of the segment BC is 5 meters, so I don't know that. So the only thing I don't know is Vf squared and Vi squared. So similarly, I want to set up conservation of energy from A to B, and then from here I'm going to break up PE into mgHA, KE into 1/2 mvB squared. Mass cancels out. Therefore, to solve for VB squared, I'm just going to multiply both sides by 2, because I need to get rid of that 2 in order to get VB squared by itself. So you notice here I'm keeping VB squared by itself because A is VF squared minus VI squared, right? VI being VB here because it starts at B, and then VF will be at point C, which I'll find in just a second. So here, if you punch this in, 2 times 9.8 times 5, you'll get 98. So we already know the initial velocity square at point B. So VI square here will be 98. Well, I don't know what VF square is, but once again, I can use the same strategy as I did in the previous method. I can say that all the kinetic energy at point C will be converted to potential energy in the spring. Well, I'm just going to break it up. 1/2 mv at point C square equals 1/2 kx square. The halves cancels out. In that case, if I were to solve for vc square, I need to divide both sides by m. So the numerator stays as kx square. And then I need to divide both sides by m, so therefore m goes in the denominator on the right side. So here, k being 2,000, x being 0.3, I want to square that, and then divide it by the mass. So vc square, you notice here, I'm not square rooting anything, I'm just keeping vc square and vb square, because I need these terms in their square form, okay? And that vc square is going to be 60, so I know vf, once again, we start at point b, and we end at point c. So VC is my final, so I'm just going to go ahead and plug that in. So wherever VF square is, which is the same as VC square here, I'm going to plug in 60. And then the initial speed square, which is 98, I'm just going to plug that in. So if you take 60 minus 98 and divide it by 10, 2 times 5 is 10, you get a value of negative 3.8. Okay, now that we have AX, I can just plug it back into there. So once again, numerator is now substitute out for negative 3.8, and then the denominator is negative 9.8, and then other than that, you get the same coefficient, which is 0.39. So again, there's different strategies. As long as you're consistent with your work and hopefully your calculator works on point, you should get the same value. All right, part C. It says here, how far up the incline does the block return? So keep in mind, A is going to go from A to B, it's going to lose some energy to C, and then it's going to compress the spring, and the spring pushes back, and then as it goes across from C to B, it loses some more energy, and it'll go back up. Okay, so here I'm gonna treat the initial reference frame from the spring when it gets compressed, and it'll shoot it back out, and then final being the final height, because it'll have to come to a stop at some point. Okay, but you notice here my HF is shorter than H here because it's losing energy, so it cannot come back, to point A, right? So I think that's common sense. It goes down, loses energy, compresses, and that P spring will convert to KE, and then it goes across, which loses energy, and then all of it, the remaining energy will be converted now to PE, which is a shorter height. Well, here I'm just going to get to it. What I want to say is I want to say the initial mechanical energy, which is stored in the spring, minus the work as it goes across C to B now, right? It's going from right to left now. And then all of that energy that's left over will be converted to PE due to gravity. So that's what I'm saying. The initial mechanical energy, which is in the spring now, minus the work that it's going to happen from C to B, which is, and the minus sign here tells you that energy is taken away from the system, right? Mechanical energy is taken away from the system, which equals to the leftover, which is MEF. So I have PE spring initial minus work due to friction, which is equal to PE due to gravity final. And well, there's PE gravity final because that is the only thing, because it's going to come back and it's going to stop, so there's no KE and all that good stuff. All right, other than that, in order to find HF, I'm just going to expand both sides of the equation here. 1/2 PE due to the spring is just 1/2 kx squared. And then the work due to kinetic friction is simply the force of kinetic friction times the displacement. The displacement here is just called L, again, which is the length from C to B or B to C. That's your delta x, but delta x really in this case is just called capital L. All right, PE due to gravity's final is going to be mgHF. And HF is what we're trying to find, so therefore I'm just going to go ahead and break FK by definition is mu k times F of n, and that's the only thing different. 1/2 kx squared stays the same, L stays the same, the right side stays the same, but as you saw earlier in part B, F of n is vector pointing upward along segment BC, and then therefore that equals to the magnitude F of G. Here, all I did, is I substitute out for Fn for F of G, but F of G is mass times gravity, and that's it. Other than that, I'm just going to plug values in. The 1/2 stays, K is 2000, X is 0.3, don't forget to square that, and then mu K, we already found mu K in part B, which is 0.39, mass is 3, G once again here is 9.8. It's positive because I already the way I have it set up, I'm already telling you that the work due to friction is quote unquote negative. So don't plug in a negative here, plug in a positive. Otherwise, if you plug in a positive here, the negative sign here will make that a positive, which contradicts then you're saying you're adding energy to the system, and that's not true. You're taking mechanical energy away from the system. Okay, L being 5, M being 3, G being 9.8, HFRs are unknown, and if you simplify the first term, you should get about 90. The second term here, you should get about 57.33, and then 3 times 9.8 is 29.4, and if you subtract 90 from 57.33 and then divide 29.4 to solve for HF, you'll get a value of about 1.1 meters, and that's our answer. Now, if you don't like that strategy, I like this one, but this one you have to be able to visualize it, right? Here, I'm actually going to start at point A. I know whatever energy you have at point A hits, it's going to go ahead and come down here. It's going to go across BC. It compresses it, but then it has to go back across the section. So really, it's going to go from BC and then C to B. So really, it's going to go across the segment twice. So what I'm saying here is I'm going to take the initial potential energy in the system due to gravity, because that's it, right? It's not moving, so there's no KE. There's no spring at point A, so there's no PE spring. So there's this PE due to gravity. I want to subtract it. There's a 2 in the front here. The 2 in the front is because it's going to go from B to C, which is one time, and then it's going to go back from C to B where it loses energy, which is twice. Well, the force is the same, the displacement is the same, so the work due to friction just occurs twice, and all of that will give me the final PE. So that's all. So it's like spending money, like you have a certain amount of money, you went to the same store twice, you drop the same amount of money twice, so therefore the leftover is your remaining. All right, and that I'm just going to break it up. That was out of order. PE due to gravity initially is just mgHA. I'm on a minus 2 because it goes across that segment twice. The work due to friction here is just F of K times L, and then PF is just mgHF, and then I want to break FK up into mu K F of N, but Fn is mg, but F of G is just mg here. And as you can see, mass cancels out. Sorry, I think my animations are all off in the segment because I was trying to add this on to a different way to do it. All right, on that, here you have everything. G, HA, mu K, which is 0.39, G is 9.8, L is 5, and G is 9.8. And if you simplify all this on the left side, you get 10.78, and then G being 9.8. And as you can see here, if you take this on your calculator and you solve for HF, so to solve for HF, divide both sides by 9.8. I'm running out of space here, so just take my word for it. If you take 10.78 divide 9.8, you'll get 1.1, which is the same answer as I have over here. So your answer for part C is 1.1 meters. Okay, other than that, I hope that helps. Stay nerdy, don't be wild.